Calculating the pH of a weak base solution. Okay, so we can take the same approach to this as we do for calculating the pH of a weak acid. So the first step should always be to write your base dissociation expression. So for any base, it doesn't matter what the base is, even if it's a strange one that you've never met before, like allantoin, whatever that is, okay? I know that a base is going to accept a proton from the water to form its conjugate acid. So whatever the formula of the base is, I care not, right? You can just stick an H plus on it for accepting the proton, right? And that gives you the formula of the conjugate acid. And then what is left of the water after it has given up an H plus, it's just going to have hydroxide left. So that is your generic expression for the dissociation of any weak base, something a little bit like this. So then you can write your base protonation constant expression, which is going to just look like an acid ionization constant expression. And of course, you don't include the water in that because water is a pure substance, so has no concentration associated with it. So concentration of products raised to the power of their stoichiometric coefficient will just be concentration of conjugate acid, concentration of hydroxide, if I can find the right button, divided by the concentration of the weak base will equal whatever that base protonation constant is. So just as an FYI, pH is based on the negative log of the concentration of H+. We are going to solve for the concentration at equilibrium of hydroxide. So just bear in mind, don't get so caught up in the math that you forget that we're solving for the concentration of hydroxide. So to get pH, you're going to have to, from that, either calculate the concentration of hydronium or calculate pOH and then convert that to pH. Okay, so what we should do then is write our expression for our protonation of our base, so whatever that was, N3O3 NH2, and I'm going to do myself a favor and just control copy that because I don't want to have to type it out again. Okay, so that is going to accept a proton from our water to form its conjugate base. So again, just going to copy and paste the formula. So if I add a proton to that, it won't be NH2, it'll be NH3. And we have to add one to the charge. So that is the formula of my conjugate base. And I'm also generating hydroxide. Okay, so there we have it then. Let's put in a little equilibrium arrow here. And we've been given the value of the base protonation constant. So we can go ahead and write our Kb expression. Kb is going to be the concentration of my conjugate acid, like so. Copy paste for the win. Times the concentration of hydroxide. I'm going to have to move this over a little bit. Divided by the concentration of my weak base. Haha! And that numerical value for Kb has been given to me in the question as 9.12 times 10 to the power of minus 6. So we're going to come back to that later. First of all, we're going to do our ice table or rice table, whatever you prefer. So reaction, initial concentrations, change in concentration, and equilibrium concentration. So weak base, conjugate acid, and last but not least, hydroxide. So let's fill in the information we know. We know the initial concentration of our weak base from the question is 1.3 molarity. We know that we initially start with 0 of our conjugate acid having been formed and approximately 0 hydroxide. We are assuming that autoionization of water is going to be negligible. So what's the change? So as this reaction proceeds towards equilibrium, it is going to be primarily the reaction is primarily going to be going in the forwards direction. The rate of the forwards direction will be greater than the rate of the reverse direction because mostly base is going to be converted into conjugate acid and hydroxide until we reach that equilibrium point. So the change in concentration of my weak base is going to be minus X, depending on how much it ionizes. And for every 1 mole of weak base that ionizes, it's going to make 1 mole of conjugate acid and 1 mole of hydroxide. So to work out my equilibrium concentration, so I just add down each column. So my equilibrium concentration for my weak base will be 1.3 minus X. My equilibrium concentration for my conjugate acid will be X, and my equilibrium concentration for my hydroxide will be X. And this is the thing that we are interested in solving for so we can work out pH. Then when we're just going to stuff these equilibrium concentrations in terms of X into our equilibrium constant expression. So that's going to be X is the concentration of our conjugate acid, X is our concentration of hydroxide, and 1.3 minus X will be our concentration at equilibrium of our weak base. And we know that this is going to equal our base protonation constant, which in this case is 9.12 times 10 to the power of minus 6. So 9 times out of 10, you can probably simplify this somewhat. If X is very small, which it usually is, it's going to be like 0.00 blah, 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 right? We can apply what's called the X is small approximation. So we can ignore that minus X term right there. So I am going to rewrite this, assuming that X is small. The only caveat is we have to check this, okay? So my KB expression is going to be X squared over 1.3 equals 9.12 times 10 to the power of minus 6, okay? So I can now solve for what X equals very simply with just a little bit of an algebraic rearrangement. So X is going to be the root, not easy to do, I'm going to have to draw that in a minute, of 1.3 times 9.12 times 10 to the power of minus 6. So I'm going to have to draw my crummy little square root shape, something a little bit like this. My apologies for my bad drawing. Okay, so X, which remember is standing for the concentration of hydroxide, is going to be, according to my calculations, 0.003443. That will probably do in terms of sig figs, because we've only got 2 sig figs for the initial pH, and we're asked to round our answer to 1 decimal place. So what we should do to be good chemical citizens is check that the X is small approximation is valid, okay? So the key to this, there's a couple of ways you can check it. One is check the percent ionization. If we're less than 5% ionization, so that means the equilibrium concentration of hydroxide, which is X, what we just worked out, is less than about 5% of the initial concentration of our weak base. So obviously times that by 100 to get to a percent. If that's less than 5%, that's telling us really there's not enough of an ionizer that X makes any difference whatsoever compared to the initial concentration of our weak base. So let's calculate that 0.003443 divided by 1.3 and then times 100. That gives me about 0.00 many zeros. 0.26%. There we go. 0.2. Again, that is going to be less than 5%, so that is fine and dandy. Another way you can check that is just looking at the number that you subtracted it from, right? And think about sig fig. So we subtracted X from 1.3, right? On the bottom of the KB expression, 1.3 minus X. And so if X is 0.003443, how many sig figs is 1.3 to 2, right? To 2 sig figs, well, that's still 1.3. So X is small is good, is what I'm saying. X is small is valid. Yay. Okay, so you should really do that check just to make sure. So the final thing is we have to convert concentration of hydroxide to pH. So there's 2 ways you can do this, right? You could take, let's call this method 1, okay, which is that we're going to use the ionic product for water, Kw, which is coming from the autoionization of water. So water plus water gives hydronium plus hydroxide, okay? So the waters cancel out in the equilibrium constant expression, and you just get something along the lines of this, and that equilibrium constant is 1 times 10 to the power of minus 14. So what you can do if you know the concentration of hydroxide is rearrange and solve for the concentration of hydronium. Whoop, whoop. So concentration of hydronium then is going to be that Kw1 times 10 to the power of 14, minus 14 even, divided by the concentration of hydroxide that we just worked out, which was 0.003443, and that will give me my concentration of hydronium, and that shakes out to be 2.9 blah blah times 10 times 10 to the power of minus 12. Okay, that makes sense. Because we've got a reasonably high concentration of our hydroxide, and as we know, there's an inverseness to that, so the more hydroxide it yields, the less hydronium there is, and vice versa. So then I could just go ahead and calculate pH equals minus log concentration of hydronium, what we just worked out. So that is going to be minus the log of that 2.933 times 10 to the power of minus 12. That's going to be a number that shakes out to be about 11.5. And here's your check, right? We've got a weak base. We're expecting a pH greater than 7. It's greater than 7. That sounds good to me. So that's method 1. Method 2, which is the one I usually use because it's quicker and you're less likely to stuff it up in your calculator, is use the relationship between pKw, okay? pKw, pH, and pOH. The only problem with this is sometimes you can like sort of forget what you're doing halfway through and make an error, because pOH is minus the log of the concentration of hydroxide, which is what we calculated. So we can calculate our pOH minus log of the 0.003443, and that gives us a number for pOH that comes out to be 2.5. Okay, so this is the problem with doing it this way. So I'm warning you so you don't make this error. That sounds like pH, right? But that would be a very acidic pH. We know we have a base here because the problem is pOH is based on the concentration of hydroxide, not hydronium. So we have to use the pKw. Remember, P is just minus log. So the pKw expression for the ionic product of water is that the pH plus the pOH, if I could type, that'd be great, equals 14. So the math is a little bit simpler if you do it this way around, but it is a little bit error prone because now I can work out my pH is just 14 minus the pOH that I just calculated. So 14 minus 2.5 is going to give me that 11.5. So you can do it either way. Whatever works for you will be fine. So just pick a method that works for you and stick to it.